Welcome to Science for Sleep, where wonder and calm meet. Each night we drift through galaxies, oceans, and mysteries of the natural world, not to startle, but to soothe. So, take a deep breath. Let curiosity slow your thoughts, and fall asleep to the sound of discovery. Wonders of the Milky Way. Look up at the night sky on a clear evening, and you will see thousands of tiny points of light scattered across the darkness like diamonds thrown onto black velvet. But what you are seeing is just a whisper of something far greater, something so vast and so ancient that the human mind struggles to contain its enormity. You are looking at your home, a great spiral of stars spinning through the void. A cosmic island containing hundreds of billions of suns, each one a potential harbor for worlds we have never seen. This is the Milky Way, our galaxy, and within its sweeping arms lies a treasure chest of wonders that defy imagination. From clouds of gas where stars are born in violence and beauty, to the corpses of dead suns crushed into objects so dense that a spoonful would weigh more than a mountain, from planets made of diamond to stars that dance together in eternal embrace. The Milky Way holds mysteries that have haunted humanity since we first gained the awareness to ask where we came from and where we are going. Tonight, we embark on a journey through 101 of the most spectacular, terrifying, beautiful, and strange wonders that exist within our galactic home. This is not just a tour of space, but a voyage into the very heart of creation itself. A story written in light and darkness, in fire and ice, in birth and death. The tale begins not with distance measured in miles, but in time measured in millions of years. Not with places you can touch, but with phenomena that exist on scales so grand they make our entire world seem like a grain of sand on an infinite beach. Prepare yourself for a documentary unlike any other, because we are about to explore the complete story of the 101 greatest wonders of the Milky Way. And by the time this journey ends, you will never look at the night sky the same way again. The heart of darkness, deep in the very center of our galaxy, hidden behind curtains of dust and gas that block our view with visible light. There exists something so powerful and so strange that for decades, scientists refused to believe it could be real. This is Sagittarius, a star, the supermassive black hole that sits at the gravitational heart of the Milky Way, like a spider at the center of its web. This monster contains the mass of more than 4 million suns compressed into a space smaller than the orbit of Mercury, and its gravity is so intense that nothing, not even light itself, can escape once it crosses the invisible boundary called the event horizon. The black hole spins through space, pulling everything nearby into a deadly spiral, heating the doomed matter until it glows with X-rays and gamma rays, before vanishing forever beyond that point of no return. For thousands of years, humans looked toward the constellation Sagittarius without knowing that lurking there in the galactic center was this cosmic predator, this hole in the fabric of space and time itself. The black hole does not simply sit quietly waiting for victims to stumble into its grasp, but actively shapes the destiny of our entire galaxy, holding together the great wheel of stars with its immense gravitational pull. Stars orbit this central beast at speeds reaching thousands of miles per second. And by watching their motion, astronomers finally proved beyond doubt that something invisible and incredibly massive must be commanding their paths. One star named S2 completes an orbit around Sagittarius, a star, in just 16 years. Racing through space so fast that Einstein's theory of relativity becomes necessary to describe its motion accurately. The black hole itself remains invisible, because by definition, nothing can escape from within its event horizon to bring us information. But the chaos it creates in the surrounding region makes its presence unmistakable. Matter falling toward the black hole forms an accretion disk, a swirling maelstrom of superheated gas that shines brightly even though the black hole itself remains dark. Sometimes the black hole feeds quietly, sipping on the thin gas between the stars, but at other times it devours whole stars that wander too close, ripping them apart with tidal forces and consuming them piece by piece. The death scream of a star being destroyed by a black hole can light up an entire galaxy for weeks or months as the stellar material burns with its final fire. Our own supermassive black hole is relatively quiet right now, but evidence suggests that in the past it was far more active, blazing with the light of millions of suns as it feasted on abundant gas and dust. The region immediately surrounding Sagittarius, a star, is one of the most extreme environments in the entire galaxy. A place where the normal rules of physics are pushed to their absolute limits. Time itself runs slower near the black hole because gravity warps the fabric of space-time, meaning that a clock near the event horizon would tick more slowly than one here on Earth. If you could somehow survive near a black hole, you would age more slowly than people far away. And if you watched the universe from that vantage point, you would see events in the distant cosmos unfolding in fast forward. The study of Sagittarius, a star, earned scientists the Nobel Prize in Physics because it confirmed one of the most bizarre predictions of Einstein's general relativity and revealed that supermassive black holes lurk at the centers of most large galaxies. This wonder sits 26,000 light-years away from Earth, meaning the light we see from that region today actually left on its journey when our ancestors were still painting pictures on cave walls. The black hole continues its patient existence, spinning in the dark, waiting for its next meal, the eternal heart of darkness around which our entire galaxy revolves. The stellar nursery of Orion. If the galactic center represents death and destruction, then the Orion Nebula represents birth and creation in their most spectacular form. This vast cloud of gas and dust hangs in space like a cosmic womb. And within its glowing folds, new stars are being born right now in the present moment, following a process that has continued for billions of years. The nebula sits roughly 1,300 light-years from Earth, close enough that we can see it with the naked eye as a fuzzy patch in the sword of the Orion constellation. But powerful telescopes reveal it as one of the most beautiful and complex structures in the entire night sky. The Orion Nebula glows with a soft greenish-pink light, produced when intense radiation from young hot stars ionizes the surrounding hydrogen gas, making it fluoresce like a giant neon sign in space. The nebula spans about 24 light-years across, and within this relatively small volume, hundreds of stars are currently forming from the gravitational collapse of dense clumps of gas and dust. The process of star formation begins when some disturbance, perhaps a shock wave from a nearby supernova explosion, or the gravitational influence of a passing gas cloud, causes a region of the nebula to start contracting under its own weight. As the gas falls inward, it heats up and spins faster, forming a rotating disk of material around a growing central core. The temperature and pressure at the center continue to increase until finally the core becomes hot enough and dense enough for nuclear fusion to ignite. And at that moment, a new star is born, switching on like a cosmic light bulb and beginning its journey through the stellar life cycle. The Orion Nebula contains stars at all stages of this birth process, from dense dark knots that are just beginning to collapse to fully formed young stars that blaze with ultraviolet light. Some of the youngest stars are still surrounded by their birth cocoons, thick disks of dust and gas from which planets may eventually form, giving us a window into how our own solar system must have looked more than 4.5 billion years ago. The four brightest stars at the heart of the nebula are called the trapezium, and these young, massive stars pump out so much radiation that they are actively destroying the nebula that gave them birth, evaporating the gas and eventually dispersing the cloud into interstellar space. This creates a strange cycle where the birth of stars ensures the destruction of the stellar nursery, guaranteeing that eventually the nebula will fade away and leave behind only a cluster of newborn stars. The Orion Nebula also contains strange structures called proplyds, which are protoplanetary disks around young stars that we can actually see being shaped by the intense radiation environment. These disks are being slowly photoevaporated by the harsh light from the trapezium stars, creating beautiful teardrop shapes as the outer gas is stripped away, while the inner disk remains protected by its own density. Within these disks, dust grains are colliding and sticking together, beginning the long process that eventually leads to the formation of rocks, asteroids, and planets. The nebula is also home to violent stellar outflows. Jets of gas shot out from the poles of young stars at speeds reaching hundreds of miles per second. These jets plow into the surrounding nebula, creating shock waves and bow shocks that glow with their own light. The Orion Nebula has been observed by humans for thousands of years. But only with modern telescopes have we been able to appreciate its true nature as a stellar factory, where the raw materials of the universe are being assembled into new suns and possibly new worlds. Every time we look at the Orion Nebula, we are witnessing creation in action, seeing the universe remake itself as it has done countless times before, and will continue to do long after humanity is gone. The nebula reminds us that the universe is not static, but dynamic, constantly tearing down and building up, destroying and creating in an endless cycle. The light we see from the nebula left on its journey to Earth around the time the Roman Empire was beginning to fade, and the stars being born there now will continue to shine long after our sun has grown cold and dark. This wonder represents hope and renewal, the promise that even in a universe governed by entropy and decay, new things can always emerge from chaos. The pillars of creation. Within the Eagle Nebula, some 7,000 light-years distant from Earth, there exist three towering columns of gas and dust that have become perhaps the most famous astronomical image ever captured. A picture so iconic that it has appeared on everything from postage stamps to museum walls. These are the pillars of creation, vast structures stretching several light-years in length, where new stars are being sculpted from the raw materials of the cosmos, like statues being carved from marble. The pillars appear in images as dark, dense fingers reaching upward against a glowing background of ionized gas. And their shape is created by a process called photoevaporation, where intense ultraviolet light from nearby massive stars eats away at the surface of the denser cloud, while the interior remains protected. The pillars are not permanent features, but temporary sculptures created by the ongoing battle between gravity trying to collapse the gas into stars and radiation pressure trying to blow it away into space. At the tips and along the surfaces of the pillars, small dense knots called evaporating gaseous globules, or EGGs, contain embryonic stars that are still forming inside their dusty cocoons. These protostars are hidden from our view at visible wavelengths, but can be detected using infrared telescopes that peer through the dust to see the warm, glowing cores within. The pillars of creation are slowly being destroyed by the very stars they are helping to create, as the ultraviolet radiation from newly formed massive stars erodes the pillars at a rate of thousands of miles per hour. This means the pillars will eventually disappear, though the process will take many thousands of years from our perspective. In fact, there is evidence that a nearby supernova explosion may have already destroyed the pillars. But because the Eagle Nebula is so far away, the light from that destruction has not yet reached Earth. So we continue to see the pillars as they were 7,000 years ago, preserved in the light that has been traveling through space all this time. The famous image of the pillars of creation was first captured by the Hubble Space Telescope in 1995, and it immediately became an icon representing humanity's exploration of the cosmos. The image shows not just scientific data, but also profound beauty, revealing that the universe creates art on a scale and with a palette that no human artist could ever match. The colors in the image correspond to different elements and temperatures, with red showing sulfur, green showing hydrogen, and blue showing oxygen, creating a false color view that helps scientists understand the composition and physics of the nebula. Later images from more powerful instruments have revealed even more detail, showing delicate structures within the pillars and catching glimpses of the young stars hidden inside. The pillars also shoot out thin jets of material, evidence of the violent activity associated with star formation, where material falling onto a growing protostar is redirected by magnetic fields and shot out along the rotation axis at high speeds. These jets plow into the surrounding nebula and create small shock waves that can trigger further star formation, meaning that stars can actually help create the next generation of stars. The Eagle Nebula as a whole is a massive star-forming region containing thousands of stars in various stages of development. But the pillars of creation have become its most famous feature because they encapsulate in a single image the drama and grandeur of cosmic creation. When you look at the pillars of creation, you are looking at time and process frozen in a single moment, seeing structures that are simultaneously being created and destroyed, that exist in a delicate balance between competing forces. The pillars teach us that beauty in the universe is often transient, that the most spectacular structures are frequently the most temporary, shaped by violence and destined for destruction. They also remind us of our own origins, because the atoms in our bodies were once part of clouds like this, forged in the nuclear furnaces of stars and scattered through space to eventually become part of planets and living things. The pillars of creation stand as monuments to the cycle of death and rebirth that governs the cosmos, where nothing is permanent, but everything is connected through time and process. The Crab Nebula and its pulsar. On the 4th day of July in the year 1054, astronomers in China and the Middle East recorded the sudden appearance of a brilliant new star in the constellation Taurus. A visitor star so bright that it could be seen in broad daylight for 23 days and remained visible at night for nearly 2 years before slowly fading from view. What those ancient observers witnessed was not a new star, but the death of an old one. A catastrophic supernova explosion that marked the end of a massive star's life and the birth of one of the strangest objects in the entire galaxy. Today we call the remnant of that explosion the Crab Nebula, and it sits roughly 6,500 light-years away from Earth. A tangled web of glowing filaments expanding outward at millions of miles per hour from the site of the original explosion. The nebula spans about 11 light-years across now and continues to grow larger every day as the debris from the explosion races outward into interstellar space. The filaments of the Crab Nebula glow with a complex mixture of colors representing different elements that were created in the star and then scattered by the explosion, including hydrogen, helium, carbon, oxygen, nitrogen, and heavier elements all the way up to iron. But the most remarkable feature of the Crab Nebula is not the expanding shell of debris, but what lies at its heart. The crushed core of the original star, compressed by the supernova into an object just 12 miles across, but containing more mass than our entire sun. This is a neutron star, matter compressed to densities so extreme that a teaspoon of it would weigh more than a mountain. And it spins on its axis 30 times per second, while producing beams of radiation that sweep across space like a cosmic lighthouse. We call this rapidly spinning neutron star a pulsar. And the Crab pulsar was one of the first such objects ever discovered, providing proof that these theoretical extreme objects actually exist in nature. The pulsar spins so fast and so precisely that it can be used as a cosmic clock, though it is gradually slowing down as it pours energy into the surrounding nebula. The rotation rate is slowing by about 38 nanoseconds per day, which sounds tiny, but over centuries and millennia will add up to measurable changes. The energy pumped out by the pulsar powers the entire nebula, making it glow much more brightly than it otherwise would from the fading heat of the original explosion. The pulsar creates a powerful magnetic field, trillions of times stronger than Earth's magnetic field. And this field accelerates particles to nearly the speed of light, creating intense beams of radiation across the entire electromagnetic spectrum from radio waves to gamma rays. The Crab pulsar is bright enough that we can detect its pulses not just in radio waves but in visible light, X-rays, and even gamma rays, making it one of the most studied objects in all of astronomy. The environment around a pulsar is one of the most extreme in the universe, with magnetic fields strong enough to distort the shapes of atoms and gravitational fields so intense that time runs noticeably slower than in normal space. If you could somehow survive a visit to the surface of a neutron star, you would weigh billions of times more than you do on Earth, crushed instantly by gravity. The pulsar's magnetic field channels material from the surrounding nebula onto the magnetic poles, creating hotspots that glow with X-rays and produce the pulsed emission we detect from Earth. The discovery of pulsars revolutionized our understanding of stellar death and proved that general relativity's predictions about extreme states of matter were correct. The Crab Nebula and its pulsar provide a perfect laboratory for studying physics under extreme conditions, allowing scientists to test theories about matter, gravity, and magnetism in regimes that cannot be reproduced in any laboratory on Earth. The nebula continues to fascinate astronomers because it shows observable changes over timescales as short as weeks or months, with knots and filaments in the nebula brightening and fading as they are buffeted by the pulsar wind. Some filaments appear to be moving at speeds greater than half the speed of light, an illusion created by the geometry of the expanding shell, but still dramatic to observe. The Crab Nebula also produces mysterious flares of gamma rays that come and go unpredictably, suggesting that something complex is happening in the interaction between the pulsar and the surrounding nebula. This wonder demonstrates that even death in the universe can be spectacular and beautiful, that the end of one star's life provides energy and material for the next generation of stars and planets. Every atom of oxygen you breathe and every atom of iron in your blood was created in a star and scattered through space by a supernova explosion like the one that created the Crab Nebula, connecting us directly to these cosmic catastrophes. The Tarantula Nebula. Near the edge of the Milky Way, in a companion galaxy called the Large Magellanic Cloud, there blazes a stellar nursery so vast and so luminous that if it were located at the same distance as the Orion Nebula, it would cast shadows on the ground at night and be visible during the day. This is the Tarantula Nebula, named for its appearance in telescopes where glowing filaments spread out like the legs of a giant spider. And it represents star formation driven to an extreme that is rarely seen in our home galaxy. The Tarantula Nebula spans nearly 1,000 light-years across and contains enough gas to make hundreds of thousands of stars. And at its heart sits a cluster of some of the most massive and most luminous stars known anywhere in the universe. This central cluster, called R136, contains dozens of stars, each weighing more than 50 times the mass of our Sun. And some of these monsters approach or may even exceed 200 solar masses, pushing against the theoretical limits of how massive a star can become. These enormous stars burn through their nuclear fuel at a prodigious rate and produce so much energy that their radiation pressure nearly tears them apart, blowing huge amounts of material off their surfaces in powerful stellar winds. The Tarantula Nebula glows with intense ultraviolet light as these massive stars ionize the surrounding hydrogen gas, creating a bubble of hot plasma several hundred light years across. The entire nebula shines with the light of millions of suns. And even though it sits roughly 160,000 light years away in the Large Magellanic Cloud, it is easily visible to the naked eye from the southern hemisphere as a fuzzy patch of light. The conditions inside the Tarantula Nebula are nothing like those in nearby stellar nurseries, such as the Orion Nebula, because the massive stars at its core produce such intense radiation that they completely change the character of the star-forming process. The ultraviolet light and powerful stellar winds from the most massive stars both trigger new star formation by compressing nearby gas clouds and inhibit it by heating and dispersing the gas before it can collapse. This creates a complex feedback process where star formation comes in waves, with bursts of activity followed by quieter periods as the nebula adjusts to each new generation of massive stars. Some regions of the Tarantula Nebula show pillars and structures similar to the pillars of creation, but on much larger scales, with columns of gas and dust stretching dozens of light years and containing enough material to form entire clusters of stars. The massive stars at the heart of the nebula are doomed to short, violent lives, each one destined to explode as a supernova within just a few million years of its birth. When these supernovae occur, they will pump enormous amounts of energy into the nebula, triggering shock waves that compress gas and likely spark new rounds of star formation, while simultaneously destroying nearby stellar nurseries. The Tarantula Nebula has already hosted multiple supernovae in recent history, including supernova 1987A, the closest and brightest supernova observed in modern times. That explosion occurred when a blue supergiant star, about 20 times the mass of the Sun, reached the end of its life and collapsed, creating a burst of light that temporarily outshone the entire rest of the Large Magellanic Cloud. The light from that supernova reached Earth on February 23, 1987, and astronomers around the world scrambled to observe it with every available instrument, gathering data that has since transformed our understanding of stellar death and supernova physics. The dying star had been identified on earlier photographs, allowing scientists for the first time to match a supernova explosion with its progenitor star, confirming theoretical predictions about which stars end their lives in this way. The Tarantula Nebula continues to be one of the most studied star-forming regions in the entire local universe, because it provides a nearby example of the kind of intense starburst activity that was more common in the early universe, when galaxies were younger and gas was more abundant. By studying the Tarantula Nebula, astronomers can learn about the processes that created the first generations of stars billions of years ago in the early universe. The nebula also helps us understand the ecology of galaxies, showing how star formation regulates itself through feedback mechanisms and how the most massive stars dominate the energy budget of their surroundings. The Tarantula Nebula represents star formation at its most extreme and most spectacular, a cosmic furnace where matter and energy interact on scales that humble our attempts to understand them fully. Betelgeuse, the red supergiant, in the constellation Orion, marking the hunter's right shoulder, there shines a star that has captivated human attention for thousands of years, with its distinctive reddish color and impressive brightness. This is Betelgeuse, a red supergiant star representing one of the final stages of stellar evolution for massive stars. And it is quite literally a dying star that could explode as a supernova at any moment in cosmic terms, though that moment might not arrive for another 100,000 years. Betelgeuse is enormous beyond easy comprehension, with a diameter roughly 700 times that of our Sun, meaning that if we could place it at the center of our solar system, it would extend beyond the orbit of Mars and possibly even reach Jupiter. The star's exact size is difficult to measure because red supergiants do not have sharp edges like smaller stars, but instead gradually fade into space with a fuzzy extended atmosphere. Betelgeuse is also relatively close to Earth by astronomical standards, sitting somewhere between 500 and 700 light-years away. Close enough that when it eventually explodes, it will briefly become as bright as the full moon in our night sky, and will be visible during the daytime for weeks or months. The star varies in brightness irregularly, sometimes dimming dramatically before brightening again. And in late 2019 and early 2020, it underwent an unusually deep dimming that sparked speculation in the media that it might be about to explode. Scientists later determined that the dimming was caused by a massive ejection of material from the star's surface that cooled and condensed into dust, temporarily blocking our view of the star. But the incident reminded everyone that Betelgeuse is a star on the edge, a stellar powder keg that could detonate at any time. Red supergiants like Betelgeuse are stars that began their lives with masses many times greater than our Sun and have burned through their hydrogen fuel, then their helium, and are now fusing heavier elements in their cores in a desperate attempt to stave off gravitational collapse. The core of Betelgeuse is like a cosmic onion with layers of different elements undergoing fusion at different depths, with the outermost layer fusing hydrogen, then helium, carbon, oxygen, and neon in progressively deeper shells, while at the very center, silicon is being fused into iron. Iron is the end of the line for fusion because fusing iron requires energy rather than releasing it. So once the core fills with iron, the star's energy source shuts down, and nothing can prevent the catastrophic collapse that leads to a supernova. Betelgeuse has likely already begun creating iron in its core, meaning it is in the final stages of its life, though those final stages could last for thousands of years. When Betelgeuse does explode, it will create a supernova bright enough to cast shadows at night and possibly cause temporary disruption to satellites due to the burst of high-energy radiation. But it is far enough away that it poses no real danger to life on Earth. The explosion will scatter the material of the star across many light-years of space, enriching the interstellar medium with heavy elements created in the star and in the explosion itself. A neutron star, or possibly even a black hole, will be left behind at the center of the expanding debris cloud, a tiny, dense remnant of the once enormous red supergiant. Betelgeuse rotates rapidly for such a large star, completing one rotation about every 30 years, and this rotation, combined with convection in the star's outer layers, creates a complex and turbulent atmosphere. High-resolution images of Betelgeuse have revealed enormous bright spots on its surface, each one larger than our entire Sun, created by gigantic convection cells where hot material from deep inside the star rises to the surface, cools, and sinks back down. The star also has a huge extended atmosphere and even a surrounding shell of previously ejected material, showing that red supergiants are messy and actively shed mass as they approach the end of their lives. Betelgeuse loses mass at a rate equivalent to roughly 1 Earth per year, blowing a powerful stellar wind into space that creates a bow shock where it collides with the surrounding interstellar medium. This mass loss is part of why the star will explode as a supernova, rather than collapsing directly into a black hole, because by the time the core collapses, the outer layers will have been partially stripped away. Betelgeuse has been important to many cultures throughout history, featuring prominently in the mythology and navigation practices of peoples around the world. And its name comes from Arabic and means something like the hand of the central one, or the armpit of the giant, depending on translation. Modern astronomers consider Betelgeuse a crucial target for understanding stellar evolution because it is close enough to study in detail and represents a stage of stellar life that is relatively brief but critically important for enriching the galaxy with heavy elements. The star teaches us that the brightest and most massive stars burn fast and die young, living for only millions of years compared to the billions of years that smaller stars like our Sun will enjoy. Betelgeuse reminds us of our own mortality on a cosmic scale and shows that even the seemingly permanent stars are temporary features in a universe governed by change. The Pleiades star cluster. Among the most easily recognized patterns in the night sky, visible from anywhere on Earth and prominent in the mythology of cultures separated by continents and oceans, is a small, tight group of bright blue-white stars that has been called the Seven Sisters, the Pleiades, for thousands of years. This is an open star cluster containing several thousand stars that all formed together from the same giant cloud of gas and dust about 100 million years ago, making them youngsters on the cosmic timescale, and they continue to travel through space together as a loose group bound by mutual gravity. The Pleiades cluster sits roughly 440 light-years from Earth in the constellation Taurus, and its brightest stars are hot, young massive stars of spectral type B that burn with a blue-white color and are far more luminous than our Sun. Most people can see 6 or 7 of the brightest Pleiades stars with the naked eye, and people with excellent vision under dark skies can see up to 14. But telescopes reveal that the cluster contains more than 3,000 stars, in total scattered across a region about 30 light-years in diameter. The cluster is young enough that its stars have not yet had time to drift apart and disperse into the general stellar population of the galaxy. But they are also not gravitationally bound tightly enough to stay together forever. So eventually, over hundreds of millions of years, the cluster will gradually dissolve as its members go their separate ways. The brightest stars in the Pleiades are surrounded by reflection nebulae, faint blue clouds of dust that shine with reflected starlight, creating a beautiful, ethereal appearance in long-exposure photographs. For many years, astronomers thought this nebulosity was leftover material from the cloud that formed the cluster. But we now know that the Pleiades are simply passing through a dust cloud in space and lighting it up temporarily as they go. The stars of the Pleiades are spinning rapidly, many of them rotating at speeds approaching their breakup velocity, where centrifugal force nearly overcomes gravity. And this rapid rotation is a characteristic of young stars that have not yet had time to slow down through magnetic braking. The cluster also contains brown dwarfs, failed stars that did not have enough mass to sustain hydrogen fusion and instead slowly cool and fade over time, providing important data for understanding the boundary between stars and planets. The Pleiades have been important to human cultures for as long as we have records, and almost certainly for much longer than that. The cluster is mentioned in ancient texts, including the Bible and Homer's Iliad and Odyssey. And it was used as a calendar marker by many agricultural societies because its first appearance in the dawn sky after a period of invisibility marked specific times of the year useful for planting and harvesting. The Japanese name for the cluster means united, and it features prominently in Japanese culture, even appearing on the corporate logo of Subaru Automobile Company. Various Native American tribes saw the Pleiades as 7 sisters, brothers, or children, and told stories about how they came to be placed in the sky. And similar stories exist in Australian Aboriginal cultures, African cultures, and Pacific Islander cultures. This commonality across human cultures, separated by geography and history, suggests that the Pleiades have been recognizable and meaningful to people for many thousands of years, possibly since before various human populations spread across the globe. The study of the Pleiades has been important for astronomy, because as a nearby young cluster with well-determined properties, it serves as a calibration target for measuring distances and testing stellar evolution theories. By comparing observations of Pleiades stars to computer models of stellar structure and evolution, astronomers can fine-tune their understanding of how stars work and improve their ability to interpret observations of more distant stars. The Pleiades also provide insight into planet formation, because several of the stars show evidence of circumstellar disks, regions of dust and gas that may be in the process of forming planets or may be debris left over from planet formation. These disks are difficult to detect and study, but the relative proximity and youth of the Pleiades make them ideal targets for such investigations. The cluster moves through space at about 25 miles per second relative to the Sun, traveling in a direction that will eventually take it away from Earth. Though over human timescales, the motion is imperceptible. In about 250 million years, the Pleiades will have orbited the galaxy and returned to approximately their current location, having completed one galactic year. The Pleiades represent youth and vitality in the stellar sense. A group of stars in the prime of their lives, burning bright and hot, not yet touched by age and the slow processes of stellar evolution. They remind us that stars are not born in isolation, but in groups, and that for a time at least, those siblings travel through space together before drifting apart to individual destinies. The Horsehead Nebula, rising from the edge of a bright emission nebula like a chess piece carved from shadow. The Horsehead Nebula is one of the most distinctive and most photographed dark nebulae in the entire sky. This feature sits roughly 1,500 light-years away in the constellation Orion, part of the same vast complex of star-forming regions that includes the Orion Nebula and the Flame Nebula. The Horsehead itself is a dense cloud of dust and gas that appears dark because it blocks the light from the brighter nebula behind it, creating the iconic Horsehead silhouette that astronomers recognized in early photographs. The nebula is small, measuring only about 3.5 light-years from the top of the head to the base, but its distinctive shape and beautiful contrast against the background make it a favorite target for astrophotographers and professional observatories alike. The Horsehead is actually a small part of a much larger, dark cloud that extends across this region of space, and its shape is being sculpted by radiation from nearby hot stars, particularly Sigma Orionis, a bright star system that lies just to the west of the nebula. The intense ultraviolet light from these stars is slowly eroding the Horsehead, evaporating it away from the side facing the stars and creating the sharp edge that defines the Horsehead profile. In a few million years, the radiation will have completely destroyed the nebula and dispersed its gas back into the interstellar medium. So the Horsehead is a temporary structure that exists only because we happen to live at the right time and look from the right angle to see it. Behind the dark cloud of the Horsehead itself, the bright pinkish-red glow comes from hydrogen gas, ionized by the same hot stars that are destroying the nebula. And this emission nebula is designated IC 434. Below the Horsehead, the background nebula includes regions that are actively forming new stars, though these stellar nurseries are hidden behind the dust at visible wavelengths. Infrared telescopes can peer through the dust to reveal young stars embedded in the nebula, showing that even as the Horsehead is being destroyed, New stars are being born nearby, continuing the cycle of stellar birth and death. The Horsehead Nebula became famous partly because of its striking appearance in photographs, but also because it is relatively easy to photograph, despite being challenging to see visually through amateur telescopes. The nebula requires long exposure times and hydrogen alpha filters to capture effectively, but when imaged properly, it reveals exquisite detail, including wispy structures around the horse's mane and nose. The colors in many images of the horsehead are enhanced or false color representations, with the reddish hydrogen emission contrasted against the dark dust and sometimes blue reflection nebulae in the surrounding area. The Barnard 33, which is the official designation of the Horsehead, is one of the most easily recognized dark nebulae, but the sky contains hundreds of similar features. Dark clouds that show up as apparent holes or silhouettes against brighter backgrounds. These dark nebulae are cold, dense regions of molecular gas and dust, the raw material from which new stars will eventually form, and they are among the coldest places in the galaxy, with temperatures often just a few degrees above absolute zero. Inside the densest parts of these clouds, conditions are so cold and dark that molecules can form that would be instantly destroyed in warmer environments, including organic molecules that are the building blocks of life. The Horsehead Nebula and its surroundings are rich in such complex molecules, making this region not just beautiful, but scientifically important for understanding how chemistry works in space. The nebula has been observed at virtually every wavelength of light, from radio waves to X-rays, and each wavelength reveals different aspects of its structure and composition. Radio observations show the distribution of cold molecular gas. Infrared observations reveal embedded young stars and measure the temperature of dust. Visible light shows the ionized gas and the dark silhouette. And even X-ray observations have detected emission from the hot stars that are sculpting the nebula. This multi-wavelength approach allows astronomers to build a complete, three-dimensional understanding of the nebula and its environment. The Horsehead sits in one of the most studied and most productive star-forming regions in the nearby galaxy. Part of the Orion molecular cloud complex that has given birth to thousands of stars over the past 10 million years and continues to produce new stars today. The entire complex will likely be dispersed over the next few tens of millions of years as the massive stars in the region evolve, explode as supernovae, and blow away the remaining gas. But for now, it remains a cosmic laboratory where we can study star formation in real time. The Horsehead Nebula stands as a monument to the temporary nature of beauty in the universe, a structure shaped by chance and circumstance that will exist for just a cosmic moment before being swept away. But in that moment, it has captured human imagination and reminded us that the universe creates art that no human mind could have invented. Eta Carinae, the supernova. Imposter. In the southern constellation Carina, hidden from observers in the northern hemisphere, there exists one of the most massive and most unstable star systems known to astronomy. A stellar monster that has cheated death at least once and probably multiple times, but cannot escape its doom forever. This is Eta Carinae, a binary star system containing at least one star of more than 100 solar masses, making it one of the most massive stars known, and possibly a second massive companion, all wrapped in a complex nebula created by violent eruptions from the primary star. Eta Carinae is famous for its great eruption in the 1840s, when it suddenly brightened to become the second brightest star in the entire sky, remaining extremely luminous for about 20 years before fading again to naked eye invisibility. For decades, astronomers thought this eruption might have been a supernova, but the star survived, earning Eta Carinae the nickname of supernova imposter, and launching decades of investigation into what could cause such a massive energy release without destroying the star. We now understand that the Great Eruption was a massive explosive ejection of material from the star, blowing off 10 or more solar masses in a brief period and creating the bipolar nebula called the homunculus that surrounds the star today. The homunculus nebula consists of two lobes of ejected material, expanding outward at hundreds of miles per second, and it contains enough material to make 10 or more stars like our Sun. The nebula blocks our direct view of the star system itself, so astronomers must use infrared and other long wavelength observations to study the stars hidden at the center. The primary star in the Eta Carinae system produces so much energy that radiation pressure nearly tears it apart, creating a constant struggle between gravity trying to hold the star together and radiation trying to blow it into space. This makes the star inherently unstable, prone to outbursts and eruptions as the internal structure shifts and changes. The star loses mass constantly through a powerful stellar wind that carries away the equivalent of several Earths' worth of material every year. And occasionally it sheds much larger amounts in eruptions like the Great Event of the 1840s. The companion star orbits the primary once every 5.5 years in a highly elliptical orbit. And when the companion approaches closest to the primary star, their interaction creates X-ray emission and other observable effects that have allowed astronomers to determine properties of the binary system. The nature of the companion star remains uncertain because it is hidden behind the much brighter primary and surrounded by the homunculus nebula. But it is likely itself a massive star of 30 solar masses or more. The Eta Carinae system sits about 7,500 light-years from Earth, far enough away that even when the primary star eventually explodes as a supernova, it will not pose any danger to life on Earth, though it will be a spectacular sight in the southern sky. The star may explode at any time in the next 1,000,000 years, though predicting exactly when is impossible given our limited understanding of such extreme stellar physics. When Eta Carinae does explode, it may produce one of the most powerful types of supernova known, possibly a hypernova or even a gamma-ray burst if conditions are right. A gamma-ray burst occurs when the core of a massive rotating star collapses into a black hole and produces jets of matter and energy that shoot out along the rotation axis at nearly the speed of light. If one of these jets happened to point toward Earth, it could potentially damage our ozone layer and cause extinction-level effects despite the great distance. But the probability of such precise alignment is very small. The Eta Carinae system has been important for understanding the upper limits of stellar mass and luminosity, showing that stars can exist far beyond what was once thought possible, but that such extreme stars are unstable and short-lived. The Great Eruption of the 1840s has also become a crucial test case for understanding a type of stellar explosion called luminous blue variable eruptions, where massive stars undergo periods of dramatic instability and mass loss. These eruptions may be common in the most massive stars and might represent a necessary phase of evolution before the final supernova explosion. The homunculus nebula itself has been studied in exquisite detail with modern telescopes, revealing complex structures including polar caps, a thin equatorial skirt, and numerous small-scale features created by the interaction of the ejected material with the surrounding interstellar medium. Observations of the nebula allow astronomers to reconstruct the history of the eruption and understand the physical processes that drove it. Eta Carinae sits in the Carina Nebula, a vast star-forming region containing many other massive young stars, making this one of the most energetic and most intensively studied regions of the galaxy. The Carina Nebula as a whole spans several hundred light-years and contains enough gas to make millions of stars. And it is being sculpted and eventually destroyed by the intense radiation and stellar winds from Eta Carinae and other massive stars in the region. Eta Carinae represents stellar evolution at its most extreme, showing what happens when a star forms with so much mass that it spends its entire life on the edge of self-destruction. Too massive to be stable, but held together by gravity until the inevitable moment when that balance fails and the star tears itself apart in a final act of cosmic violence. The Ring Nebula. When a star like our Sun reaches the end of its life, it does not explode as a supernova, but instead dies more gently, puffing off its outer layers in a series of thermal pulses that create an expanding shell of glowing gas. This shell, lit from within by the hot white dwarf core of the dead star, is called a planetary nebula, despite having nothing to do with planets. And among the most famous and most beautiful examples is the Ring Nebula in the constellation Lyra. The Ring Nebula sits about 2,300 light-years from Earth and appears as a nearly perfect ring or donut of multicolored gas about 1 light-year across, glowing with a soft, ethereal light that has made it a favorite target for amateur and professional astronomers alike. At the center of the ring lies a white dwarf star, the exposed core of the original star, a stellar ember about the size of Earth, but containing roughly 60% the mass of our Sun. The white dwarf has a surface temperature exceeding 100,000 degrees, hot enough that it produces intense ultraviolet radiation that ionizes the surrounding gas and causes it to fluoresce with the characteristic colors of planetary nebulae. The ring structure appears as a ring from our perspective because we are looking through a roughly spherical or cylindrical shell of gas. And along the line of sight through the edges of the shell, we see more gas than when looking straight through the center, creating the appearance of a bright ring with a darker center. The Ring Nebula is not actually a perfect ring, but a more complex three-dimensional structure, probably a cylinder or barrel shape with open ends pointed more or less toward and away from us. High-resolution images from the Hubble Space Telescope have revealed that the nebula consists of multiple nested shells and has an outer halo of fainter material that extends beyond the bright inner ring, showing that the star shed its outer layers in several distinct episodes, separated by hundreds or thousands of years. The inner ring shows fine-scale structure, including knots and irregularities that may be caused by instabilities in the ejected gas, or by interactions with material ejected during earlier or later episodes. The colors and images of the Ring Nebula correspond to emission from different elements at different temperatures, with reddish regions showing hydrogen and nitrogen, greenish regions showing oxygen, and bluish regions showing helium and ionized oxygen. These colors reveal the chemical composition of the dying star's outer layers, showing elements that were created through nuclear fusion during the star's lifetime and are now being returned to the interstellar medium. The Ring Nebula is expanding at about 12 miles per second, meaning that in a few tens of thousands of years it will have dissipated and faded from view, mixing its material with the interstellar gas to enrich future generations of stars. The white dwarf at the center will continue to cool slowly over billions of years, eventually becoming a black dwarf, a theoretical object so cold and so dark that it no longer emits detectable light. However, the universe is not yet old enough for any white dwarfs to have cooled to the black dwarf stage. So this final fate remains a prediction rather than an observation. The Ring Nebula represents the future of our own Sun, showing what will happen roughly 5 billion years from now, when the Sun exhausts its hydrogen fuel, swells into a red giant that engulfs Mercury and Venus, and possibly Earth, and then sheds its outer layers to create a planetary nebula of its own. The white dwarf left behind will be all that remains of the star that nurtured life on Earth and made our existence possible. Planetary nebulae like the Ring Nebula play an important role in the chemical evolution of galaxies because they return processed material to the interstellar medium, enriching it with carbon, nitrogen, oxygen, and other elements created through nuclear fusion. These elements are then incorporated into new generations of stars and planets, continuing the cycle of stellar birth, life, death, and rebirth that has operated since the first stars formed billions of years ago. The Ring Nebula has been observed for centuries. First discovered by the French astronomer Antoine Darquier de Pellepoix in 1785, and independently by Charles Messier, who included it in his famous catalogue as Messier 57. Early observers with small telescopes could see only the basic ring shape, but modern instruments reveal layer upon layer of complexity, showing that even the death of a star is a structured and orderly process governed by physics. The Ring Nebula's beauty comes not just from its shape, but from its colors and its context, representing a moment of transition between stellar life and stellar death. A brief flash of visibility before the cooling white dwarf fades into darkness. The nebula teaches us that death in the universe can be gentle and beautiful, not always violent and destructive, and that even a dying star can create something lovely in its final moments. Sagittarius B2 and complex molecules. Deep in the galactic center region, about 300 light-years from the supermassive black hole, there lies a vast cloud of gas and dust so rich in complex molecules that it has been called the center of molecular complexity in the galaxy. This is Sagittarius B2, a giant molecular cloud containing millions of times the mass of our Sun and serving as both a stellar nursery and a cosmic chemistry laboratory. Sagittarius B2 is famous among astrochemists because it contains more than 40 different types of molecules, including many organic compounds that are the building blocks of life. Among the molecules detected in Sagittarius B2 are water, ammonia, formaldehyde, ethanol, which is drinking alcohol, methanol, acetone, glycolaldehyde, which is a sugar, and even amino acids, which are the building blocks of proteins. The cloud also contains molecules with more exotic properties, including fullerenes, which are soccer ball-shaped carbon molecules, and polycyclic aromatic hydrocarbons, which are ring-shaped carbon compounds that may be abundant throughout the universe. The detection of these complex organic molecules in space was initially surprising because scientists once believed that the harsh conditions of the interstellar medium would quickly destroy such fragile compounds. But observations have shown that in the densest and coldest parts of molecular clouds, protected from destructive ultraviolet radiation, surprisingly complex chemistry can occur. The molecules in Sagittarius B2 form through gas phase chemical reactions and through reactions on the surfaces of dust grains, where atoms and molecules stick and can spend enough time in close proximity to react with each other. The dust grains serve as a kind of cosmic chemistry set, providing surfaces where molecules can assemble and protecting them from being torn apart by radiation. The temperature in the core of Sagittarius B2 is just a few tens of degrees above absolute zero, cold enough that even volatile substances freeze onto dust grains, creating icy coatings that can be several molecules thick. When these ices are heated by nearby forming stars, the molecules evaporate back into the gas phase, where they can be detected by radio telescopes tuned to the specific frequencies at which different molecules absorb and emit radiation. Each type of molecule has a unique spectral fingerprint, a pattern of absorption and emission lines that acts like a barcode identifying which molecule is present. Sagittarius B2 is being surveyed by radio telescopes in painstaking detail, with astronomers systematically searching for the signatures of new molecules and mapping the distribution of known molecules throughout the cloud. The cloud itself is not uniform, but contains multiple dense cores where star formation is occurring. including regions called Sagittarius B2 North and Sagittarius B2 Main that are particularly active and particularly rich in complex molecules. These cores contain forming stars that heat the surrounding gas and make it easier to detect molecules. Because warm molecules emit more strongly than cold molecules. The temperature and density structure of Sagittarius B2 is complex, with hot spots around forming stars surrounded by cooler envelopes and all embedded in the larger cold cloud. This complex structure means that different molecules are found in different regions depending on their formation and destruction pathways. For example, simpler molecules like carbon monoxide are found throughout the cloud, while more complex molecules are concentrated in the warmest and densest regions near forming stars. The discovery of alcohol and sugar molecules in Sagittarius B2 generated public interest and led to headlines about giant clouds of rum in space. Though the actual concentration of these molecules is far too low to be useful for making drinks, nevertheless, the presence of such molecules demonstrates that the chemical building blocks of life are common in the universe and that the chemistry necessary for life may occur naturally wherever conditions are right. Sagittarius B2 also contains what are called hot cores, extremely dense and warm regions with temperatures reaching several hundred degrees Kelvin, where the chemistry is particularly active and diverse. These hot cores are thought to represent an early stage in the formation of massive stars, and studying them helps astronomers understand both star formation and astrochemistry. The detection of molecules in space requires incredibly sensitive instruments because the signals are extremely weak and must be picked out from noise and interference. Radio astronomy has developed sophisticated techniques, including interferometry, which combines signals from multiple telescopes to create a virtual telescope the size of the distance between them, dramatically improving resolution and sensitivity. Observations of Sagittarius B2 have pushed these techniques to their limits and have driven the development of new instruments and methods. The cloud sits about 26,000 light-years from Earth in the direction of the galactic center, making it one of the more distant objects in our catalog of wonders. But its brightness at radio wavelengths and its rich molecular content make it relatively easy to study compared to more nearby but less active clouds. Sagittarius B2 teaches us that space is not empty, but filled with chemistry, that between the stars, matter and energy interact to create molecules of increasing complexity, and that the ingredients for life may be common throughout the universe, waiting for the right conditions to assemble into living systems. The Veil Nebula supernova remnant spread across several degrees of sky in the constellation Cygnus, looking like delicate cosmic lace or the tattered remains of a massive soap bubble. The Veil Nebula is the remnant of a supernova explosion that occurred roughly 8,000 years ago when a massive star ended its life in catastrophic collapse. The expanding shell of debris from that explosion has now spread to cover a region about 110 light-years across and continues to race outward at speeds exceeding 600,000 miles per hour, sweeping up interstellar gas and creating shock waves that heat the material to millions of degrees. The Veil Nebula is actually part of a larger structure called the Cygnus Loop, a roughly circular supernova remnant of which the veil represents the brightest and most visually striking portions. The nebula is divided into several distinct sections that have been given their own designations, including the Western Veil, the Eastern Veil, and Pickering's Triangle. But all are part of the same expanding shell viewed from different angles. The nebula glows with a complex mixture of colors representing emission from different elements at different temperatures, with red emission from hydrogen, green from oxygen, and blue from sulfur, creating a rainbow effect in color images. The structure of the Veil Nebula is incredibly complex, showing filaments, sheets, and ripples created as the supernova shockwave plows through the irregular interstellar medium. Where the shockwave encounters denser clumps of gas, it slows down and brightens, creating the intricate filigree patterns that make the nebula so beautiful. The shockwave acts like a cosmic snowplow, compressing and heating the gas it encounters, and the collision is violent enough to strip electrons from atoms, creating the ionized gas that produces the nebula's glow. Behind the main shockwave, the gas cools and recombines, creating a shell of warm material that continues to expand but no longer glows as brightly. The Veil Nebula sits about 2,400 light-years from Earth, close enough that it covers a large area of sky, but far enough that it posed no danger to Earth when the supernova occurred 8,000 years ago. If the explosion had been significantly closer, the burst of radiation and high-energy particles could have damaged Earth's ozone layer and caused extinction events, demonstrating that supernovae are not just beautiful, but potentially dangerous phenomena. Fortunately, there are no massive stars close enough to Earth that their eventual supernovae would pose a serious threat. The original star that exploded to create the Veil Nebula probably had a mass of about 20 times that of our Sun and would have been a brilliant blue-white star during its life. The star lived for only a few million years before exhausting its nuclear fuel and collapsing, compared to the 10 billion-year lifetime expected for stars like our Sun. When the core collapsed, it probably formed a neutron star, or possibly a black hole. But this remnant has not been definitively identified in observations of the nebula. The neutron star, or black hole, would have received a kick during the supernova explosion, a random push caused by asymmetries in the explosion, and it may have been ejected from the nebula entirely and could be anywhere within hundreds of light-years of the explosion site. Searches for the compact remnant have been conducted using X-ray telescopes and other instruments, but have not yet yielded a confirmed detection. The Veil Nebula continues to evolve and will eventually fade and merge with the general interstellar medium. But for now, it remains a spectacular example of a supernova remnant in its middle age. No longer the bright young remnant like the Crab Nebula, but not yet old and faint like the most ancient remnants that can barely be detected. The nebula has been an important target for studying the physics of shock waves, the chemical enrichment of the interstellar medium, and the late stages of supernova remnant evolution. Observations at multiple wavelengths, from radio to X-rays, have revealed that the nebula is a multi-temperature structure, with different regions emitting at different wavelengths depending on the local density, temperature, and composition. The X-ray emission traces the hottest gas immediately behind the shock front, where temperatures reach millions of degrees, while optical emission comes from somewhat cooler gas where temperatures are tens of thousands of degrees, and radio emission traces even cooler regions and in the magnetic fields threaded through the nebula. The Veil Nebula demonstrates that supernovae are not instantaneous events, but ongoing processes that continue to affect their surroundings for thousands or even millions of years after the initial explosion. The energy released in the supernova is gradually transferred to the surrounding interstellar medium, heating and accelerating the gas and contributing to the turbulent structure of the galaxy. Supernova remnants like the Veil also accelerate cosmic rays, high-energy particles that zoom through the galaxy at nearly the speed of light and contribute to the radiation environment of space. Some of the cosmic rays that constantly bombard Earth originated in supernova shocks, like those in the Veil Nebula, connecting us directly to these distant cosmic catastrophes. The galactic bulge. Looking toward the constellation Sagittarius on a dark summer night from the northern hemisphere, or a dark winter night from the southern hemisphere, you can see the Milky Way at its brightest and most impressive, a glowing band of light swelling to a bright irregular bulge that represents the heart of our galaxy. This is the galactic bulge, a roughly spherical concentration of old stars, bone, and dust surrounding the galactic center and extending several thousand light-years in all directions from the supermassive black hole. The bulge contains roughly 20 billion stars packed into a relatively small volume, making it one of the densest stellar environments in the galaxy outside of globular clusters. Stars in the bulge are mostly old, with ages exceeding 10 billion years. And they formed during an early burst of star formation when the galaxy was young and gas was plentiful. The bulge stars orbit the galactic center in complex patterns that differ from the orderly circular orbits of stars in the galactic disk, moving in elongated elliptical paths and crisscrossing each other in a chaotic dance governed by gravity. The bulge is not perfectly spherical, but somewhat box-shaped or peanut-shaped when viewed from certain angles, a structure created by the complex dynamics of the orbiting stars and by a bar-shaped concentration of stars that extends through the galactic center. Our galaxy is what astronomers call a barred spiral galaxy, meaning it has a central bar of stars rather than a simple spherical bulge. And this bar funnels gas toward the galactic center, where it can fuel star formation and feed the central black hole. The galactic bulge is difficult to study in detail because it is heavily obscured by dust in the galactic plane that blocks visible light and makes it hard to see individual stars. Infrared observations can penetrate this dust and have revealed the true structure and population of the bulge, showing that it contains a mix of stellar populations with different ages, compositions, and kinematics. Some bulge stars are metal-rich, meaning they contain relatively high abundances of elements heavier than hydrogen and helium, while others are metal-poor, like the oldest stars in the galaxy, suggesting multiple episodes of star formation and a complex formation history. The bulge also contains significant amounts of gas and dust, though less than in the disk, and this material is being slowly consumed by ongoing star formation near the galactic center. The region around the bulge contains several massive star-forming regions, including Sagittarius B2 discussed earlier, showing that despite its age, the bulge continues to produce new stars. The density of stars in the bulge means that stellar encounters and interactions are more common there than in the disk, and binary star systems may be disrupted by close encounters with other stars, leading to changes in orbital parameters and occasionally to mergers between stars. The bulge is also home to a large population of low-mass stars, including red dwarfs and brown dwarfs, that are difficult to detect because of their faintness, but that contribute significant mass to the total. Understanding the galactic bulge is important for understanding galaxy formation and evolution, because the bulge preserves a record of conditions in the early galaxy before the disk settled into its current structure. The chemical composition of bulge stars tells us about the history of star formation and nucleosynthesis in the early galaxy. And the dynamics of bulge stars tell us about the gravitational potential and the presence of dark matter. The galactic bulge also serves as an example for understanding bulges in other galaxies, which come in different types, including classical bulges that formed early and pseudo-bulges that formed more recently through disk instabilities. Our galaxy's bulge appears to be a combination of both types, with an old classical component and a younger pseudo-bulge associated with the galactic bar. The bulge is also a prime target for searches for exoplanets because the high density of stars means that microlensing events, where the gravity of a foreground star magnifies the light from a background star and can reveal the presence of planets around the foreground star, occur more frequently than in the less crowded disk. Several exoplanet surveys have monitored millions of stars in the galactic bulge, looking for the brief brightness changes that signal microlensing events. And these surveys have detected dozens of planets including some that are very far from their host stars or that orbit stars very different from our Sun. The galactic bulge represents the ancient core of our galaxy, the foundation upon which the disk was built. And studying it allows us to look back in time to the early epochs of galaxy formation, when the universe was younger and the conditions for star formation were very different from what we see today. Globular clusters and Omega Centauri, scattered around the Milky Way in a roughly spherical halo that extends far above and below the galactic disk. There exist about 160 ancient balls of stars called globular clusters, each one containing hundreds of thousands or even millions of stars packed into a sphere just tens of light years across. These clusters are among the oldest objects in the galaxy, with ages approaching 13 billion years, nearly as old as the universe itself. And they contain stars that formed from the primordial material of the early cosmos before it had been enriched with heavy elements from supernova explosions. The largest and most massive globular cluster orbiting the Milky Way is Omega Centauri, a spectacular object visible to the naked eye from the southern hemisphere as a fuzzy star in the constellation Centaurus. Omega Centauri contains about 10 million stars packed into a sphere roughly 150 light-years across. And the core of the cluster is so densely packed that if we lived there, the night sky would be filled with thousands of stars as bright as Venus, creating a sky that never truly gets dark. The cluster sits about 16,000 light-years from Earth and has been known since ancient times, catalogued by the Greek astronomer Ptolemy, who thought it was a single star. Observations with telescopes revealed its true nature as a vast collection of stars, and modern instruments have shown that Omega Centauri is unusual among globular clusters in several respects. Unlike most globular clusters where all the stars have very similar compositions because they form together from the same material, Omega Centauri shows a spread in metallicity, with different stars having different abundances of heavy elements, suggesting that star formation occurred in multiple episodes over a span of time. This multi-generational star formation is unusual for globular clusters and has led some astronomers to suggest that Omega Centauri is not a true globular cluster, but rather the stripped core of a dwarf galaxy that was captured and dismembered by the Milky Way long ago. The gravitational pull of the Milky Way would have stripped away the outer stars of the dwarf galaxy, leaving only the dense central core that we now see as Omega Centauri. This theory is supported by the cluster's unusual properties, including its large mass, its stellar population, and the fact that it may contain an intermediate mass black hole at its center, something not expected in normal globular clusters. The search for black holes in globular clusters has been challenging, because the clusters contain no gas that could form an accretion disk and reveal the black hole's presence through bright emission. So astronomers must instead look at the motions of stars near the cluster center and use those velocities to infer the presence of a massive dark object. In Omega Centauri, some observations have suggested that stars in the very center are moving faster than can be explained by the gravitational pull of the visible stars alone, implying a central black hole with a mass of perhaps 40,000 times that of the Sun. However, other explanations for the observed stellar motions are possible, and the existence of a central black hole in Omega Centauri remains unproven, though tantalizing. Globular clusters like Omega Centauri are important for several reasons beyond their inherent beauty. They provide laboratories for studying stellar evolution in environments very different from the solar neighborhood, where star density is low and interactions between stars are rare. In globular clusters, stars can collide and merge, creating exotic objects called blue stragglers that appear younger and bluer than other cluster stars because they have been reinvigorated by the merger. The high density also leads to frequent close encounters between stars and binary systems, resulting in a complex, dynamical evolution where heavier stars sink toward the center through a process called mass segregation, while lighter stars are pushed to the outskirts. Over billions of years, some stars gain enough energy through gravitational interactions to escape the cluster entirely, causing the cluster to slowly evaporate and lose mass. Globular clusters also serve as cosmic clocks because their ages can be determined by comparing the observed population of stars to theoretical models of stellar evolution. The oldest stars in a cluster, the ones just now reaching the end of their lives and leaving the main sequence, set a minimum age for the cluster, and in the case of the most ancient globular clusters, this age approaches the age of the universe itself. Studying globular clusters therefore provides constraints on cosmology and the history of galaxy formation. The spatial distribution of globular clusters around the Milky Way traces the shape of the dark matter halo, the invisible mass that dominates the gravitational field of the galaxy. Because the clusters orbit in the gravitational potential defined primarily by dark matter rather than by visible matter. Omega Centauri follows an eccentric orbit that takes it from about 4,000 light-years to about 16,000 light-years from the galactic center, passing through the galactic disk periodically and experiencing tidal forces that strip away some of its outer stars. The tidal tails of stars lost from the cluster have been detected extending along its orbit, providing further evidence that the cluster is slowly being dismantled by the Milky Way's gravity. Despite this ongoing destruction, Omega Centauri remains a magnificent sight and will continue to grace our skies for billions of years into the future, gradually fading as it loses mass, but remaining one of the jewels of the southern sky. The Helix Nebula. Among planetary nebulae, few are as nearby or as well studied as the Helix Nebula, a vast shell of gas surrounding a dying sun-like star, located only about 650 light-years from Earth in the constellation Aquarius. The Helix is one of the closest planetary nebulae to Earth and covers an area of sky roughly half the diameter of the full moon, making it one of the largest planetary nebulae in apparent size, though not necessarily in actual physical dimensions. The nebula appears as a complex series of nested shells and rings, with the main helix structure created by our viewing angle through a cylindrical or hourglass-shaped shell of gas. At the center of the nebula sits a white dwarf star, the exposed core of the original sun-like star, with a surface temperature exceeding 100,000 degrees Kelvin. This white dwarf produces the intense ultraviolet radiation that ionizes the surrounding gas and causes the nebula to fluoresce with colors corresponding to emission from hydrogen, nitrogen, oxygen, and other elements. The Helix Nebula is often called the Eye of God in popular culture because in some images it resembles a giant eye staring out from space, though this nickname is not used by astronomers. The nebula's structure is more complex than it first appears, with high-resolution images revealing thousands of cometary knots, small, dense clumps of gas that have been shaped by the intense radiation from the central star. These knots have bright ionized heads facing the star and fainter tails pointing away, giving them a comet-like appearance. Each knot contains enough material to fill several solar systems and may represent dense clumps in the original stellar atmosphere that survived the mass loss events that created the nebula. The cometary knots are being slowly photoevaporated by the stellar radiation, creating the tail structures that stream away from the star. The Helix Nebula also shows an outer halo of faint material extending well beyond the main shell, evidence of earlier mass loss episodes when the star was in an earlier stage of evolution. The nebula is expanding at about 20 miles per second, meaning it will continue to grow and fade over the next tens of thousands of years until it becomes too diffuse to see and merges with the general interstellar medium. The white dwarf at the center will continue to cool over billions of years, gradually fading from view as it radiates away its residual heat. The Helix Nebula represents what will happen to our Sun in about 5 billion years, when it exhausts its hydrogen fuel, swells into a red giant that engulfs the inner planets, and then sheds its outer layers to create a planetary nebula of its own. Studying the helix therefore provides insights into the future of our solar system and the ultimate fate of Earth. The red giant phase will last for several 100 million years, during which the Sun will swell to perhaps 100 times its current diameter, and its surface temperature will drop to about 3,000 degrees, giving it a deep red color. During this phase, the Sun will lose mass through a powerful stellar wind, shedding perhaps half its mass into space over the course of the red giant phase. Eventually, the core of the Sun will be exposed as a hot white dwarf surrounded by the expanding shells of ejected material, creating a planetary nebula that future civilizations, if they exist, might observe from other star systems. The Helix Nebula has been observed at virtually every wavelength, from radio to X-rays, and each wavelength reveals different aspects of the nebula's structure and physics. Infrared observations show emission from warm dust mixed with the gas, suggesting that the dying star shed not just gas but also dust during its final stages. X-ray observations reveal hot gas in the inner regions of the nebula and emission from the white dwarf itself, which has a thin atmosphere of hydrogen and helium overlying its dense interior. Radio observations trace the distribution of ionized gas and can measure the expansion velocity and mass of the nebula. The Helix Nebula has also been important for testing models of planetary nebula formation and evolution, particularly models that attempt to explain the complex shapes observed in planetary nebulae. The simple picture of a star puffing off its atmosphere in a spherical shell does not explain the observed structures, and astronomers have developed more sophisticated models involving binary companions, rotating stars, and magnetic fields to account for the diverse morphologies of planetary nebula. The helix's relatively simple structure compared to some more exotic planetary nebulae makes it a good starting point for understanding these phenomena. The nebula's proximity also makes it an excellent target for searching for molecules and dust grains in the ejecta, allowing detailed studies of the chemistry of dying stars. The Helix Nebula stands as a preview of our own star's death, a reminder that even stars have finite lifetimes, and that the Sun that has sustained life on Earth for billions of years will eventually run out of fuel and end its main sequence life. The galactic halo and high-velocity clouds surrounding the visible disk and bulge of the Milky Way, extending hundreds of thousands of light-years into space. There exists a roughly spherical halo of dark matter, old stars, and globular clusters that represents the ancient scaffolding upon which the galaxy was built. The galactic halo contains only about 1% of the galaxy's stars, but dominates the mass distribution because it is filled with dark matter, the mysterious invisible substance that makes up about 85% of the matter in the universe. The stellar halo consists primarily of old metal-poor stars that formed early in the galaxy's history, before successive generations of star formation enriched the interstellar medium with heavy elements. These halo stars orbit the galactic center in random directions rather than the organized rotation of disk stars, creating a slow, chaotic swarm that fills the space around the galaxy. The halo also contains structures called stellar streams, thin arcs of stars that represent the tidal debris of disrupted dwarf galaxies and globular clusters that have been torn apart by the Milky Way's gravity. These streams are like cosmic breadcrumbs, showing the paths of objects that ventured too close to the galaxy and were destroyed. And studying them helps astronomers understand the history of galactic cannibalism and the growth of the Milky Way through mergers within and beyond the stellar halo. Observations have revealed the presence of high-velocity clouds, vast masses of hydrogen gas moving at velocities much higher than typical for gas in the disk, and often falling toward the galactic plane from high latitudes. These high-velocity clouds contain millions of solar masses of gas and are thought to be material raining down onto the galaxy from the intergalactic medium, or possibly remnants of ancient gas clouds left over from the galaxy's formation. Some high-velocity clouds may also be gas ejected from the disk by supernova explosions and stellar winds, traveling in a galactic fountain that carries material high above the disk before it falls back down. The high-velocity cloud complex is not well understood, and determining the distances to these clouds is challenging because they contain no stars or other objects that can serve as distance indicators. Radio observations that map the 21-centimeter emission line of neutral hydrogen can trace the distribution and kinematics of high-velocity clouds. But without distance information, it is difficult to determine their true physical properties. Some recent observations have managed to estimate distances to a few high-velocity clouds. By finding faint stars projected against the clouds and determining whether the star's spectra show absorption lines from the cloud gas, indicating that the stars lie behind the clouds. These observations suggest that at least some high-velocity clouds lie in the halo tens of thousands of light-years from the disk, confirming that they are truly extragalactic material or material in the galactic fountain. One of the largest high-velocity clouds is the Smith cloud, a massive concentration of hydrogen gas on a collision course with the Milky Way disk. The Smith cloud contains enough material to make about 1 million suns worth of stars and is falling toward the disk at about 240 miles per second. It is expected to collide with the disk in about 30 million years, triggering a burst of star formation where it impacts and adding its gas to the galaxy's reservoir of star-forming material. The Smith cloud is thought to have been ejected from the disk about 70 million years ago, traveled far out into the halo, and is now falling back in a textbook example of the galactic fountain in action. The leading edge of the Smith cloud is being compressed and heated by its motion through the tenuous halo gas, creating a bow shock that can be detected in observations. High-velocity clouds may be an important source of fresh gas for the galaxy, continuously replenishing the disk's supply of hydrogen and allowing star formation to continue even as existing gas is consumed. Without some mechanism to bring in new gas from outside, the Milky Way would have exhausted its star-forming material billions of years ago, and star formation would have ceased. The existence of high-velocity clouds and the galactic fountain helps explain why star formation continues at a steady rate despite billions of years of gas consumption. The galactic halo also contains hot gas at temperatures of millions of degrees, detected through X-ray emission and absorption, that fills much of the volume around the galaxy and may contain as much mass as all the cold gas in the disk. This hot halo gas is thought to be heated by supernova explosions and stellar winds in the disk that launch hot bubbles of gas into the halo. And it may also be primordial gas left over from the galaxy's formation that never cooled and fell into the disk. Understanding the hot halo is important for understanding the baryon budget of the galaxy, accounting for all the normal matter that should be present based on cosmological models. Observations have shown that only about half the expected baryons can be accounted for in stars and cold gas, and much of the missing mass may reside in the hot halo. The galactic halo and its contents represent the frontier between the galaxy proper and the intergalactic medium, the transitional zone where the galaxy's gravity is still dominant, but where material can be exchanged with the larger universe beyond. The Canis Major Dwarf Galaxy. Until the year 2003, astronomers believed they had identified all the satellite galaxies orbiting the Milky Way. cataloging about a dozen dwarf galaxies, including the famous Magellanic Clouds and various smaller systems. Then analysis of data from the 2-micron all-sky survey revealed a previously unknown overdensity of stars in the direction of the constellation Canis Major. And further investigation showed that this was not a chance alignment, but a dwarf galaxy in the process of being torn apart and consumed by the Milky Way. The Canis Major dwarf galaxy is now recognized as the closest known satellite galaxy to the Milky Way, sitting just 25,000 light-years from Earth and a mere 42,000 light-years from the galactic center, well within the volume occupied by the galactic disk. This proximity is also the dwarf galaxy's doom because the Milky Way's tidal forces are actively ripping it apart, spreading its stars into long streams that wrap around the galaxy. The discovery of the Canis Major dwarf was surprising because it had been hiding in plain sight, obscured by the dense star fields of the galactic plane that made it difficult to recognize the overdensity of stars as a separate structure. The dwarf galaxy contains about 1 billion stars, mostly old red giants and sun-like stars, making it a significant addition to the Milky Way's mass. The galaxy has already made several orbits through the disk and has lost much of its original mass to tidal stripping, with stars being pulled away and added to the Milky Way's halo. In another billion years or so, the Canis Major dwarf will likely be completely disrupted and its stars fully mixed with the Milky Way's stellar population. The dwarf galaxy is thought to be an elliptical or irregular galaxy that was captured by the Milky Way's gravity billions of years ago and has been slowly spiraling inward ever since. Each passage through the disk accelerates the disruption process because the interaction with disk stars and gas strips away more material and heats the dwarf galaxy's stars, puffing it up and making it easier to tear apart. The tidal streams of stars lost from the Canis Major dwarf have been traced around the sky, forming structures called the Monoceros ring that encircle the Milky Way at various latitudes. These streams are like cosmic archaeology, allowing astronomers to reconstruct the orbit and disruption history of the dwarf galaxy and to probe the gravitational potential of the Milky Way. The Canis Major dwarf and similar disrupted satellites are important for understanding how galaxies grow through mergers and accretion, showing that galactic evolution is a messy process involving constant small-scale mergers rather than just occasional large events. The Milky Way has consumed dozens or hundreds of smaller galaxies over its history, and many of the stars in the halo originally belonged to these accreted systems. Identifying and studying these disrupted satellites helps astronomers understand the assembly history of the galaxy and test theories of hierarchical structure formation, where large galaxies are built from smaller building blocks. The Canis Major dwarf also raises questions about how many other dwarf galaxies might be lurking undetected in the galaxy, hidden by dust and crowded star fields. Recent surveys have discovered several additional ultra-faint dwarf galaxies, systems so small and sparse that they contain fewer than 1,000 solar luminosities and are extraordinarily difficult to detect. These ultra-faint dwarfs may represent the low-mass end of the galaxy mass function, the smallest structures that can still be called galaxies, and they are important for testing dark matter theories because their mass is dominated by dark matter with very little normal matter. The discovery of new satellites continues as more sensitive surveys cover the sky, and current models predict that the Milky Way should host hundreds of small satellite galaxies, most of them too faint to have been detected yet. Each discovery adds another piece to the puzzle of galactic formation and evolution, showing that galaxies are not isolated islands, but parts of a complex ecosystem of structures interacting and merging over cosmic time. Mira, the wonderful variable star. Among the thousands of variable stars visible from Earth, few have been studied as long or have proven as important for astronomy as Mirandans, a red giant star in the constellation Cetus that changes brightness dramatically over the course of about 11 months. Mira was the first variable star of its kind to be recognized. Discovered in 1596 when the Dutch astronomer David Fabricius noticed that a star he had been observing suddenly vanished from view. Over the following decades, observers realized that the star was not disappearing, but fading and brightening in a regular cycle. And in 1642, Johannes Hevelius gave the star its name Mira, meaning wonderful or astonishing. Mira varies in brightness by a factor of more than 1,000, reaching second magnitude at its brightest when it is easily visible to the naked eye and fading to 10th magnitude at its dimmest when a telescope is required to see it. This enormous variation is caused by pulsations in the star's atmosphere, where the entire star expands and contracts over a period of roughly 330 days. As the star expands, it cools and dims, and as it contracts, it heats up and brightens, creating the observed cycle. The pulsations are driven by instabilities in the star's outer layers, where hydrogen is being ionized and recombining, creating a valve-like mechanism that builds up pressure and then releases it in a cyclic manner. Mira is a red giant star near the end of its life, with a mass similar to that of our Sun, but a diameter that varies between about 400 and 500 times the solar diameter, larger than the orbit of Mars. The star is old, roughly 6 billion years old, and has exhausted the hydrogen fuel in its core and is now fusing helium into carbon and oxygen in a shell surrounding the inert core. The pulsations that make Mira variable also drive mass loss, with the star shedding about 100,000th of a solar mass per year through a stellar wind. This mass loss is gradually eroding the star, and in another million years or so, Mira will have lost enough mass that it will shed its outer layers completely and become a planetary nebula with a white dwarf at its center, following the same path that awaits our Sun. Mira has a binary companion, Mira B, a white dwarf that orbits the primary star once every 400 years at an average distance of about 70 astronomical units. The presence of the companion was discovered in 1923 and has been studied intensively because material from Mira's stellar wind is being accreted onto the white dwarf, heating it up and creating an accretion disk that emits X-rays. The interaction between the two stars creates complex structures in the gas surrounding the system, and observations have revealed an S-shaped tail of material stretching behind Mira for a distance of several light years. This tail was discovered in 2007 using ultraviolet observations and represents material that Mira has shed over the past 30,000 years as it moves through space at about 120 kilometers per second relative to the surrounding interstellar medium. The tail is created as Mira's stellar wind interacts with the thin gas of the interstellar medium, similar to how a comet's tail is created by the interaction of solar wind with cometary material. The tail contains enough material to make about 3,000 Earths and provides a record of Mira's mass loss history over tens of thousands of years. Mira-type variable stars, named after this prototype, are common in the galaxy and represent an important stage of stellar evolution that all low to intermediate mass stars will pass through. These stars are important for several reasons, including their role in enriching the interstellar medium with carbon, nitrogen, and other elements created through nuclear fusion and transported to the surface by convection. The stellar winds from Mira variables are also important sources of dust in the galaxy because the cool temperatures in their atmospheres allow molecules and dust grains to condense. And these dust grains are then carried into space by the stellar wind. Observations of Mira variables have also been important for measuring distances in the universe because they follow a period luminosity relationship similar to but distinct from that of Cepheid variables, where the period of variability is correlated with the star's intrinsic brightness. By measuring the period and apparent brightness of a Mira variable, astronomers can determine its distance, making these stars useful as standard candles for mapping the structure of the galaxy and nearby galaxies. Mira itself has been used to calibrate this relationship and to study the physics of stellar pulsation, and it continues to be an important target for observers. The star has been observed across the electromagnetic spectrum from radio to X-rays, revealing different aspects of its structure and the physics of its atmosphere and wind. Mira represents the twilight years of stars like our Sun, showing what the Sun will become in about 6 billion years when it exhausts its hydrogen fuel and begins the long process of dying. The North America Nebula. Among the largest and most recognizable nebulae in the sky, the North America Nebula earns its name from its resemblance to the shape of the North American continent, complete with a prominent Gulf of Mexico region. This vast emission nebula sits about 1,600 light-years from Earth in the constellation Cygnus, part of the same large molecular cloud complex that includes the nearby Pelican Nebula and numerous other star-forming regions. The North America Nebula spans about 50 light-years across and glows primarily with the red light of hydrogen alpha emission, produced when ultraviolet radiation from hot young stars ionizes the hydrogen gas and causes it to fluoresce. The nebula is bright enough to be detected with binoculars under dark skies, though its large size means it has low surface brightness and can be challenging to see visually. Long exposure photographs reveal the nebula's complex structure with bright emission regions mixed with dark dust lanes that create the geographic features that give it its name. The Gulf of Mexico region is particularly prominent, created by a foreground dark cloud that blocks our view of the bright emission nebula behind it and creates a striking silhouette. The star or stars responsible for ionizing the North America Nebula have been debated for decades because the nebula is embedded in a region with many hot young stars, and determining which ones contribute most to the ionization is not straightforward. Recent observations suggest that the primary ionizing source is probably a massive star or cluster of stars hidden behind the dust of the nebula, energetic enough to ionize a region 50 light-years across, but obscured at visible wavelengths by the intervening material. Infrared observations that can penetrate the dust have revealed numerous young stars embedded in the nebula, showing that star formation is ongoing in this region and that the nebula harbors the next generation of stars being born from the collapsing molecular cloud. The North America Nebula is part of a much larger structure that includes the adjacent Pelican Nebula and extends across several degrees of sky, all part of the same giant molecular cloud complex called the Cygnus X region. This region is one of the most active star-forming areas in the nearby galaxy and contains enough gas to make millions of stars. The entire complex is being sculpted by radiation and stellar winds from massive stars, creating intricate structures of pillars, globules, and cavities where the hot gas and intense radiation pressure of young stars battles against the gravity of the molecular cloud, trying to collapse and form more stars. The dark dust lanes that create the Gulf of Mexico and other features in the nebula are dense concentrations of gas and dust where future stars may form, protected for now from the ionizing radiation by their high density. These dark regions appear as silhouettes against the brighter nebula, but infrared and radio observations show that they contain complex molecular gas with temperatures just a few degrees above absolute zero, the coldest material in the galaxy. Within these cold, dark clouds, molecules form that would be quickly destroyed by radiation in more exposed environments, including organic molecules and the building blocks of life. The North America Nebula has been a favorite target for amateur astrophotographers because its large size and relatively high brightness make it accessible to small telescopes and cameras. and because its distinctive shape is immediately recognizable. Professional astronomers have used the nebula to study the physics of ionized gas, the interaction between stars and their natal clouds, and the process of triggered star formation, where the expansion of ionized regions compresses nearby molecular gas and triggers new episodes of star formation. The nebula demonstrates that star formation is a self-regulating process, where the birth of massive stars creates conditions that both promote and inhibit further star formation, shaping the evolution of molecular clouds over millions of years. The radiation and winds from massive stars gradually eat away at the molecular cloud, dispersing the remaining gas and eventually shutting down star formation once all the available material has been consumed or blown away. This process takes several millions of years, and the North America Nebula is currently in the middle of this cycle, with active star formation ongoing, but with large regions already cleared of gas by previous generations of stars. In a few million years, the nebula will fade as the ionizing stars age and die, and the remaining gas is dispersed, leaving behind a cluster of young stars no longer embedded in the cloud that gave them birth. The North America Nebula stands as a monument to the ongoing cycle of stellar birth and death that has operated throughout galactic history. A reminder that the matter in the universe is continuously recycled through stars and returned to space to form new stars and possibly new worlds. Fast radio bursts from the magnetar SGR 1935. In the year 2007, astronomers examining archival data from the Parkes Radio Telescope in Australia made a discovery that would launch a new field of observational astronomy. They found a brief, intense burst of radio waves that lasted just a few milliseconds, but carried as much energy as the sun emits in several days. And the signals showed the characteristic frequency dispersion caused by traveling through ionized gas over a vast distance. This was the first fast radio burst, or FRB, a completely unexpected type of astronomical transient that has since become one of the most exciting and puzzling phenomena in modern astrophysics. For over a decade, the origin of fast radio bursts remained mysterious, with dozens of theoretical explanations proposed but no definitive answer. Some FRBs appeared to be one-time events, while others repeated, complicating efforts to understand their nature. The breakthrough came in 2020, when the Canadian CHIME telescope detected a fast radio burst from within our own galaxy, specifically from a known magnetar, designated SGR 1935 plus 2154. This was the first time an FRB had been detected from a source in the Milky Way, and it immediately proved that at least some fast radio bursts are produced by magnetars. Magnetars are neutron stars with extraordinarily strong magnetic fields, up to 1,000 times stronger than typical neutron stars and 1,000 trillion times stronger than Earth's magnetic field. These magnetic fields are so intense that they distort the very structure of atoms and can power violent eruptions of X-rays and gamma rays as the field lines shift and reconnect. The magnetar SGR 1935 is located about 30,000 light-years from Earth on the other side of the galaxy, and it has been observed to emit repeated bursts of X-rays and gamma rays as its magnetic field undergoes violent reorganization. On April 28, 2020, the magnetar emitted an especially powerful burst that was detected by multiple satellites as a blast of X-rays and gamma rays. And within milliseconds, radio telescopes including CHIME detected an intense burst of radio waves associated with the same event. This was the smoking gun that proved magnetars can produce fast radio bursts. Though important questions remain about how the bursts are generated and whether all FRBs come from magnetars or whether other sources also exist. The radio burst from SGR 1935 was much less energetic than FRBs detected from distant galaxies. leading to the conclusion that if typical extragalactic FRBs are produced by magnetars, they must involve even more powerful eruptions or some mechanism to focus the energy into a narrow beam pointed toward Earth. The detection of an FRB from the Milky Way also allowed for the first time a direct association between an FRB and a specific type of object, confirming that neutron stars can be sources of these mysterious bursts. Magnetars are rare, with only about 30 known in the entire galaxy, and they represent a brief phase in the life of some neutron stars when the magnetic field is at its peak strength. The magnetic field decays over time, so magnetars are young neutron stars, typically less than 10,000 years old, that have not yet had time to lose their extreme magnetism. The field stores enormous amounts of magnetic energy that can be suddenly released in what are called magnetar flares, brief intense bursts that light up the magnetar in X-rays and gamma rays, and apparently sometimes in radio waves. The mechanism that converts the magnetic energy into radio waves is not fully understood, but it likely involves the acceleration of particles to nearly the speed of light and the generation of coherent radio emission through some form of master process. The discovery that magnetars can produce FRBs has implications for understanding the broader population of fast radio bursts detected from distant galaxies, suggesting that wherever massive stars end their lives as supernovae and create neutron stars, some fraction of those neutron stars will become magnetars capable of producing detectable radio bursts. This means FRBs can be used as probes of star formation and stellar death across the universe. And because the radio bursts show dispersion caused by electrons in the intergalactic medium, they can also be used to map the distribution of matter between galaxies. Each FRB acts like a cosmic lighthouse, with its signal modified by all the material it passes through, allowing astronomers to study the otherwise invisible ionized gas that fills the space between galaxies. The study of fast radio bursts and magnetars represents one of the most exciting areas of current astrophysics research, with new discoveries being made regularly and fundamental questions about the physics of extreme magnetic fields and neutron stars still to be answered. The Sagittarius Dwarf. Elliptical galaxy, hidden from view for most of human history, concealed behind the dense star fields of the galactic center, there orbits a dwarf galaxy that is currently in the process of being torn apart and consumed by the Milky Way. This is the Sagittarius Dwarf elliptical galaxy. Discovered only in 1994, despite being one of the nearest companions to the Milky Way at a distance of about 70,000 light-years from Earth and just 50,000 light-years from the galactic center. The Sagittarius Dwarf contains several hundred million to a billion stars, making it more massive than many other dwarf satellite galaxies, but still tiny compared to the Milky Way, which contains several hundred billion stars. The dwarf galaxy was discovered by analyzing the motions and colors of stars in the direction of the galactic center, revealing a population of stars moving together in a way that couldn't be explained as part of the Milky Way structure. Follow-up observations showed that this population formed a distinct galaxy, being stretched into long tidal streams by the Milky Way's gravity. The Sagittarius Dwarf has already made several complete orbits through the Milky Way, passing through the galactic disk and emerging on the other side, and each passage strips away more of its stars and gas. The tidal streams created by this disruption have been traced completely around the Milky Way, forming a ring structure that wraps around the galaxy multiple times, like a tangled thread wound around a ball. These streams are some of the longest coherent structures in the galaxy, extending across the entire sky and containing stars that will eventually become part of the Milky Way's halo. The discovery of the Sagittarius Dwarf and its tidal streams revolutionized our understanding of the Milky Way's structure and history. because it showed that the galaxy is actively consuming smaller satellites and that significant structures in the halo are the result of this ongoing cannibalism. Some astronomers estimate that 10% or more of the Milky Way's halo stars originally belonged to the Sagittarius dwarf or similar accreted satellites, meaning that the galaxy has grown significantly through mergers over its history. The orbit of the Sagittarius dwarf is nearly polar, meaning it passes through the galactic disk at high angles, rather than orbiting in the disk plane. And this orbit carries it through regions of different density and gravitational potential that accelerate its disruption. The dwarf galaxy contains multiple stellar populations, including old metal-poor stars similar to globular cluster stars and younger, more metal-rich stars, indicating that star formation occurred over an extended period in the dwarf galaxy before it was captured by the Milky Way. Several globular clusters are known to be associated with the Sagittarius dwarf, originally formed within the dwarf galaxy, but now being stripped away and added to the Milky Way's globular cluster system. This explains some oddities in the properties of certain Milky Way globular clusters that didn't seem to fit with the others, because they were not formed in the Milky Way, but were captured along with the Sagittarius dwarf. The gradual destruction of the Sagittarius dwarf provides a real-time laboratory for studying galaxy interactions and tidal disruption, processes that are believed to be common in the universe, but difficult to observe in detail at great distances. By mapping the positions and velocities of stars in the tidal streams, astronomers can reconstruct the orbit of the dwarf galaxy over the past several billion years and predict its future evolution. Models suggest that in about 100 million years, the Sagittarius dwarf will make its next passage through the galactic disk. And in less than a billion years, it will be completely disrupted with its stars fully mixed into the Milky Way's halo. The interaction between the Sagittarius dwarf and the Milky Way may also have effects on the disk, with simulations suggesting that passages of the dwarf through the disk could trigger star formation and create ripples and warps in the disk structure. Some researchers have proposed that features in the Milky Way's disk, including the warp at its outer edge, may be caused by the gravitational influence of the Sagittarius dwarf and other satellite galaxies. The existence of the Sagittarius dwarf and other satellite galaxies being destroyed by the Milky Way demonstrates that galaxy evolution is an ongoing process and that galaxies are not static structures, but dynamic systems constantly changing through interactions, mergers, and accretion. The Milky Way is built from the accumulated debris of dozens or hundreds of smaller galaxies consumed over billions of years. And this process continues today with the Sagittarius dwarf and other satellites. Understanding this process is important for understanding galaxy formation and evolution across cosmic time, because hierarchical structure formation models predict that all large galaxies are built through the merger and accretion of smaller systems in a bottom-up process that starts with small structures and builds larger ones over time. The planetary nebula, NGC 6543, among the hundreds of known planetary nebulae, NGC 6543, better known as the Cat's Eye Nebula, stands out as one of the most complex and most beautiful, with a structure so intricate that it has challenged astronomers' understanding of how dying stars shed their outer layers. The Cat's Eye Nebula sits about 3,000 light-years from Earth in the constellation Draco and consists of a bright central region surrounded by multiple concentric shells and symmetric features that create an appearance resembling a cat's eye when viewed with powerful telescopes. At the center lies a white dwarf star, the exposed core of a sun-like star that reached the end of its life and shed its outer layers about 1,000 years ago. The white dwarf has a surface temperature exceeding 50,000 degrees Kelvin and produces intense ultraviolet radiation that ionizes the surrounding gas and causes it to fluoresce with a rainbow of colors corresponding to emission from different elements. The cat's eye shows emission from hydrogen, helium, nitrogen, oxygen, and other elements, creating concentric shells of different colors in false color images. The complexity of the nebula's structure suggests a complex mass loss history with multiple episodes of ejection, separated by hundreds or thousands of years, each one creating a new shell that expands outward and interacts with previously ejected material. The central bright region is surrounded by at least 11 concentric rings or shells visible in deep images, evidence that the mass loss occurred in a series of thermal pulses rather than as a single smooth event. These pulses occur when helium fusion in a shell around the core briefly ignites, creating a runaway reaction that causes the star to brighten and expand, ejecting material before the star settles down and the process begins again. The cat's eye also shows a number of bipolar features, including jets and ansae, meaning handles or ears, that extend in opposite directions from the central region. These symmetric features are thought to be created by the interaction between the slow wind from the dying star and a faster wind ejected later, with the shape being influenced by rotation or possibly by the presence of a binary companion. Many planetary nebulae show bipolar or multipolar structures that cannot easily be explained by the simple model of a single spherical star ejecting its atmosphere. And the presence of binary companions that influence the mass loss through gravitational effects or through accretion onto the companion is now thought to be common. The Cat's Eye Nebula has been observed at multiple wavelengths, from radio to X-rays, with each wavelength revealing different aspects of its structure and physics. X-ray observations show hot gas in the central cavity, with temperatures exceeding 1,000,000 degrees, heated by the fast wind from the white dwarf crashing into slower-moving material ejected earlier. Radio observations trace the distribution of ionized gas and can measure the expansion velocity of the nebula, which is about 10 miles per second for the outer shells. Optical observations show the intricate structure of the shells and the detailed emission line spectrum that reveals the chemical composition and physical conditions in the gas. The cat's eye has been important for testing models of planetary nebula formation and for understanding the physics of stellar winds and shocks. The nebula's multiple shells and complex structure have been reproduced in computer simulations that attempt to model the interaction of multiple winds and the effects of asymmetries in the mass loss. High-resolution images from the Hubble Space Telescope have revealed that even the smooth-looking regions of the nebula actually contain fine-scale structure, including knots and filaments, showing that the mass loss is turbulent and chaotic rather than smooth and orderly. The Cat's Eye Nebula demonstrates that the death of a sun-like star is not a simple process, but involves complex instabilities, multiple mass loss episodes, and interactions between different components of the stellar wind. The nebula will continue to expand and fade over the next tens of thousands of years, eventually dispersing and merging with the interstellar medium, while the white dwarf at its center cools over billions of years. The material in the nebula, including the carbon, nitrogen, and oxygen, visible in emission lines, was created inside the star through nuclear fusion and is now being returned to space, where it will eventually be incorporated into new generations of stars and planets. The Cat's Eye Nebula reminds us that stars do not live in isolation, but participate in the galactic ecology, taking in primordial hydrogen and helium and returning enriched material that makes possible the formation of rocky planets and ultimately life. The Serpens South Star Cluster, hidden within a dark cloud of gas and dust about 1,300 light-years from Earth, there lies a cluster of infant stars so young that many are still forming from the gravitational collapse of their natal molecular cloud. This is the Serpens South Star Cluster, discovered in 2008 using infrared observations. that could penetrate the obscuring dust and reveal the warm glow of protostars within. The cluster contains several dozen young stars and protostars packed into a region just a few light years across, representing a snapshot of star formation caught in the act. The stars range in age from objects that are still accreting material and growing to slightly older stars that have cleared away their birth cocoons and begun their lives as main sequence stars. The Serpens South Cluster is part of a larger, star-forming region called the Serpens Molecular Cloud, which contains multiple sites of active star formation and enough gas to make thousands more stars. The cluster was discovered during the Spitzer Space Telescope survey of the galactic plane, which revealed hundreds of previously unknown star-forming regions by detecting the infrared emission from warm dust heated by young stars. Serpens South appeared as a bright infrared source with no corresponding visible light source, indicating that it was deeply embedded in dust, and follow-up observations confirmed that it contained a rich cluster of forming stars. The discovery of Serpens South and similar deeply embedded clusters demonstrated that much of the star formation in the galaxy is hidden from optical observers and can only be studied using infrared and radio wavelengths that penetrate the dust. The cluster shows a high degree of alignment in the outflows from young stars, with jets and winds from many of the protostars pointing in similar directions, suggesting that the magnetic field threading through the molecular cloud has influenced the star formation process by setting a preferred axis. This alignment is not expected in standard models of turbulent star formation, and has led to renewed interest in understanding the role of magnetic fields in regulating star formation. The protostars in Serpens South are still surrounded by disks of gas and dust that will likely form planets, giving astronomers a window into the earliest stages of planet formation. Observations of these disks show that they contain complex organic molecules, including methanol and formaldehyde, the same kinds of molecules detected in comets in our solar system, suggesting that the chemical composition of protoplanetary disks may be similar across different star-forming regions. The Serpens South Cluster is also a site of triggered star formation, where the birth of one generation of stars has compressed nearby mass and triggered the collapse of new stars. This can be seen in the structure of the molecular cloud, which shows dense cores arranged in a pattern suggesting that a shock wave has passed through the region, perhaps from the stellar wind or supernova of a nearby massive star. Triggered star formation is thought to be common in star-forming regions and may lead to a cascade where star formation propagates through a molecular cloud over millions of years. The Serpens South region contains not just low-mass stars like the Sun, but also intermediate-mass stars and possibly some massive stars, creating a diverse stellar population that will eventually disperse as the remaining gas is consumed or blown away. The massive stars will live only a few million years before exploding as supernovae, enriching the region with heavy elements and possibly triggering yet another round of star formation. The study of young clusters like Serpens South is important for understanding the initial mass function, the distribution of stellar masses that results from the star formation process. Theory predicts that the IMF should be universal, producing the same distribution of stellar masses in all environments. But observations are needed to test this prediction. By counting the stars of different masses in young clusters and comparing to the theoretical IMF, astronomers can determine whether star formation works the same way everywhere, or whether environmental factors influence the outcome. Serpens South has been observed with multiple facilities, including Spitzer, Herschel, and ground-based radio telescopes to map its structure and probe the properties of the protostars and their disks. These observations have revealed that the cluster is still actively forming stars, with new protostars appearing in subsequent observations, showing that star formation is an ongoing process rather than a single, instantaneous event. The cluster will continue to evolve over the next few million years as more of the molecular cloud collapses into stars, and as the existing stars clear away the remaining gas through their winds and radiation. Eventually, the molecular cloud will be dispersed, and the cluster will emerge as a young open cluster, similar to the Pleiades, no longer embedded in the cloud that gave it birth. Over hundreds of millions of years, the cluster will gradually disperse as its stars drift apart and mix with the general stellar population of the galaxy. But for now, Serpens South represents a stellar nursery in full operation, a cosmic maternity ward where the next generation of stars is being born.